Hello everyone, welcome to my presentation entitled A Multi-Layer Software-Defined Architecture with Model Predictive Control Variable Frequency Critical Self-Switching Based Power Module for High-Performance Electric Vehicle Energy Conversion. I'm Zhou, a postdoctoral research associate from Columbia University. My advisor, Matthias Prindle, is an associate professor at Columbia University. So I would like to introduce the outline of my presentation. Firstly, I will provide the background and the introduction of our research field. Then, a concept of software-defined multi-layer control architecture is developed for the electric vehicle energy system. Then, based on the hierarchical control architecture, 3 applications of the energy conversion interfaces are demonstrated, including single-phase onboard EV charging, 3-phase off-board EV charging, and motor traction inversion systems. The corresponding experimental results are then provided to validate the theoretical analysis. Finally, the merits of the proposed multi-layer software-defined system are concluded. So this research is mainly focusing on the power electronics to improve the performance of electrified energy conversion systems. The left figure shows the relationship between the degree of electrification and the fuel efficiency improvement. With the increase of electrification, the fuel burning efficiency is improved accordingly. Also, as is shown in the right side of the figure, the total stock of the electric vehicle is largely increased in the past 10 years. So we could see that the more electrified energy conversion is a growing trend. The electrification of the energy conversion contributes to the reduction of the greenhouse gas emissions. Based on the background, the power electronics techniques are crucial to realize the electrification system. So for the power electronics techniques, it is mainly leveraging the power converters to transfer electrified energy among AC and DC formats with different voltage current specifications. The applications of power electronics can be widely used in solar, battery, wind power, grid utility, electric motor, and so on. Based on the different types of the current, the main components of power converter can be classified into DC-DC converter, DC-AC inverter, AC-DC rectifier, and AC-AC converter. Also, to regulate the voltage and current in the energy conversion system, different control methods can be applied, including proportional integral derivative control, model predictive control, intelligent control, and so on. For the hardware components, a typical power electronics system includes the power switches, gate drivers, sensing circuit, and digital controller. So our research in this project is mainly focusing on the energy conversion system in the electric vehicles. Left side of the figure shows the typical energy conversion structure inside the electric vehicle. The energy conversion system mainly includes 4 parts. First one is the DC to AC motor traction inverter to drive the electric motor. Second one is the AC to DC rectifier for the onboard battery charger. Third one is the DC to DC converter for the voltage adjustment among different interfaced power blocks, such as the DC bus to battery side or various DC electronics loads. The fourth one is the AC to DC plus DC to DC off-board charger. The last one is typically configured out of the electric vehicle as a direct connection to the battery side from the grid utility. And the fast charger has higher power rating than the onboard charger due to the volume or size limitation within the electric car. Our research is trying to reconfigure the EV energy conversion system with a software-defined concept by leveraging advanced control and design techniques. So the software-defined architecture is introduced in this slide. The holistic diagram is shown in the left figure. This is a hierarchical system including 3 layers. First one on the top side is the application function layer. This layer is configured to provide the high-level control functions for the different interfaced applications in the electric vehicle energy conversion system, such as the DC load, 3-phase grid, single-phase grid, battery, and motor. The second one on the bottom side is the elementary module layer. This layer is composed of different number of identical power modules, Each power module is equipped with advanced local controllers, such as model predictive controller and the variable frequency controller. The model predictive controller is functioned to receive the reference from the top layer and stabilize the output voltage and current of each power module with improved dynamic performance. The variable frequency controller is aimed at reducing the switching losses with desired switching frequency. The third one in the middle is the interconnection management layer. This layer is the core part that is responsible for the management between the top and bottom layers. Specifically, the required number of energy conversion stages, power converter topology, and the number of power modules in each converter are configured in this layer. So among the three layers, the power conversion block is mainly composed of different number of the elementary power module. Left figure in this slide shows the specific compositions of each power module. So it is composed of a model predictive controller, variable frequency critical soft switching controller, and hardware components. The model predictive controller is responsible for stabilizing the output voltage and current of the power module. Compared with the conventional PID control, the model predictive control has its own merit of better dynamic performance. The frequency controller is functioned to adjust the switching frequency to achieve the soft switching operation. Doing so, the power losses are reduced and the energy conversion efficiency can be improved. The hardware components include upper-lower switches, switch side inductor, upper-lower side of the output capacitors, and sensing circuits. They are combined with the control algorithms to perform a complete energy conversion block. So specifically for the model predictive control, we implemented the advanced output voltage current control in an explicit way to improve the computation efficiency. That is to say, we leverage a multi-parametric toolbox to generate the piecewise affine functions in offline, and then execute the online searching through a binary search tree configured in the toolbox. Doing so, we could implement the model predictive control optimization problem within 7 to 8 microseconds, which enables a control frequency of more than 20 kHz. Besides the model predictive control, we also implemented a variable frequency controller for each power module to achieve a soft switching operation for the upper and lower switches. The motivation of this frequency controller is to reduce the losses occurred during the energy conversion process. The basic principle of variable frequency controller is to adjust the switching frequency according to the averaged inductor current and make sure the peak and valley current ripple points are positive and negative respectively. The experimental waveforms on the right side is consistent with the sketch figure on the left side in this slide. So by doing this, the energy conversion efficiency can be improved by more than 3%. After a general introduction of the multi-layer software-defined structure, 3 applications are tested in the electric vehicle system based on the proposed concept. The first application is a single-phase grid-connected converter, which can be applied as an onboard charger. The circuit topology is shown on the right side. It is composed of 1 elementary power module on the DC-DC side and 2 modules on the DC-AC side. The corresponding control architecture is shown on the left side. In the application function layer, a single-phase PLL controller, grid-side current controller, DC-side constant voltage and constant current controllers are configured to derive the high-level references for each of the local power modules. So in the elementary module layer, the local model predictive controller in each module will follow the high-level references to stabilize the output voltage and current. By following the multi-layer control architecture, the dynamic performance can be improved with the model predictive control. Also, the energy conversion efficiency is increased with frequency controller. So different from the single-phase grid interface, another application of 3-phase grid-connected system is demonstrated in this slide. This kind of 3-phase grid connection is suitable for the off-board fast charging system with higher power rating. Instead of 2 elementary power modules connected in parallel, 3 modules are connected to the grid utility to come up with the circuitry topology on the right side of this slide. So also 3-phase PLL algorithm, grid current controller, and DC side current voltage controllers are configured in this application function layer. And 3 modules on AC side and 1 module on the DC side are following the high-level references in the elementary module layer. So besides the grid-connected applications in the previous 2 slides, another important interface is motor traction in the electric vehicle system. On the right side of the slide shows the motor traction inverter topology based on 3 elementary power modules connected in parallel. So different from the grid connection to absorb the power from the grid utility, this kind of motor traction inverter is responsible for driving the electric motor by utilizing the power from the battery side. So in the application function layer, the speed and torque controllers are configured on the AC side. So to compare between the former 2 grid connected applications and this motor traction interface, the main difference is from the high-level control algorithms in the application function layer. So the function of each local power module are identical to follow the high-level references. This kind of multi-layer concept enables the reconfigurability of the EV energy conversion system to be extended to various types of applications. And the redundant power electronics design procedures can also be saved accordingly. So after the introduction of 3 applications of the software-defined electric vehicle energy conversion architecture, some experimental results are shown in this slide. So on the right top side shows the single-phase and 3-phase grid current, voltage, and battery side current and voltage waveforms captured directly from the scope. And on the right bottom side shows the torque and speed waveforms by applying some reference steps from the motor side. So to conclude for this research project, we proposed a reconfigurable multi-layer software-defined architecture for the electric vehicle energy conversion system. The dynamic performance of the power converters are improved with the local model predictive controller, and energy conversion efficiency is also increased with the variable frequency soft switching operation. Also for the power conversion application, they all configured with the non-isolated topology, which saves the cost with smaller size. Thanks for your attention.